Okay, now we are recording. So let's add the standard libraries, include standard input output. Okay, include what else? malloc. Okay, malloc, and we will see what else later. Okay, so we have two possibilities. We either cover probing, and I think that will take the remaining hour. Now, for probing is easier because we don't have a dynamic list. We don't need dynamic lists. We need only to use the array and search for the next value. Okay, and also what your colleague said last week about deleting stuff. So how do you want to start? Let's see. Can I create a I will start a new poll. Do you want to start with deleting stuff and so I will give you a poll now to do. You see the results is probing 70 votes and 10 votes for delete. So let's start probing. In previous weeks, we always took a structure that didn't have a dynamic field. And last week, I showed you that if you have at least one dynamic field, you need to implement a copy method, something similar with a copy constructor or equals, because the standard equals will do a shallow copy. So let's take for today something that has that, okay? It has a dynamic field. So we want to store still messages, okay? Yeah, let's say we have error codes. Okay, error messages. Okay, maybe we have a system and it's generating error messages. So I will go for a dynamic field here, which is the message, the text itself. Yeah, let's call it text. And it's a dynamic field, okay? And for code, last week we used an array of charts, which was the barcode of a product, like something you can find easily in a store. So for today, let's go for a number, okay? So let's say ID, okay? Each error message has an unique ID. And we want to store them in a hash table by using probing. Okay, so this is the structure for the messages. Now, because the hash table will be based entirely on an array, it's easy to define it. We don't need a node. That was for chaining, because in chaining you had an array list of lists. So here we have just an array list of error messages. So structure, this will be our hash table. Okay, in this case. So it's a dynamic array because at some point we need to resize it from the same reasons. It will get full. So at some point we will not be able to insert new error messages into that hash table. So that's why we want to create a dynamic array. So what's the type, what's the value inside the array? Error messages. Okay, it's a dynamic array. So asterisk, and this is the table. Okay, this is the pointer to the table. And each time we play with an array, we need to handle also the number of elements. Okay, so number of values. Okay, so we need this. Now, let's not forget to initialize them. Even if you do this later, this can save you from a lot of problems later if you forget to initialize them. So once again, this is null, okay, ID, we can define it -1, and you will understand why. -1, because we already talked, this is the way that we will use in order to identify if a slot here is empty, or we can use it, okay? Otherwise, it means it's occupied. So this will be our way of flagging that some elements in the table are free, or some spaces, slots, whatever, okay, by checking the ID of that error message. Okay, so this is the hash table. That's it. It's not so complex as we have seen last week. Let's start with a function that will create an error message. Okay, so once again, we split this in small pieces. So error message is init message. Okay, so we need a const char asterisk message and ID. Okay, so because it's a dynamic field, the text, so this will be our message. We need to create space for that. So message dot text equals char asterisk malloc of string length of message +1. Okay, multiply with size of string length. Okay. I need to include the string.h. This is the common effect when you don't have the library. We need to add it here. It will not recognize string-based functions. So string.h. Okay, so add the string.h library here on top. Now it's okay. Let's copy the text. String copy. So message dot text and the message. Okay, and let's not forget about the ID equals ID. Okay, so in this way we init the message. Okay, what else do we need? So we know how to create a message. Sorry. Yeah, return. Yeah. Like I said, I will put a disclaimer. So generally I will forget to return, but I will eventually realize that when we will test the method in main, the compiler will give me a compiler error. So I think that's why I don't stress about this, because I know the compiler will show me that I forgot to return. So that's why I consider it's not important. Okay, so we know how to create a message. Let's print a message. Being here, let's cover all possible cases. So this is print message. And because we have a dynamic field, error message, it means that we need to check if we have a text there. So if message dot text different than null, then printf, okay, error %s, okay, with ID %d. So here I have the message dot text and message dot ID. Now else printf error or no error with ID equals %d. And here I'm printing only the message ID. Okay, so this is print message. And what I was telling you last week, because at some point we need to copy an error message from, I don't know, from something we receive, we need to copy over a location in our table, in the hash table. We need to avoid shallow copy, because anytime someone will write something like message equals, let's say, message 2, here you will have a shallow copy, because equals will copy paste the pointer and the ID over the other. So now you will have two messages with the same pointer. And I don't know what will happen. If one message will delete that text, the other one will remain with the dangling pointer. Remember, it's a pointer which is not null, but it's pointing to an address that doesn't belong anymore to us. So if you try to use that pointer, you'll get a runtime exception. So let's do a function called copy. Okay, so copy message. And obviously the first one is the destination. It's like string copy. Okay, error messages, yeah. Okay, sorry for the plural here. So let's leave them error messages. Okay, so this is the destination and this is the source. Error messages source. Now in this story, which structure is changing? The destination or the source? Which article? So because it's changing, we change something into its variables, text and ID, we need to pass it by address. Okay, so we want to copy the source. Now, in order to copy the ID, that's simple. It's a pointer now, this one. So I will start with that, ID. Now, if we want to copy the text, once again, we need to create space, but maybe we have some space. So let's avoid the memory leak. Avoid memory leaks. Okay, so let's do our check. Okay, instead. So if destination text different than null, it means we already have some text here. So free destination text. Okay, so in this way we avoid the memory leak. And after that, we do this. Destination text equals char asterisk malloc with string length of source dot text +1 and string copy destination text of source dot text. Okay, so now we have our own equals, let's say. Okay, and in this way we avoid the shallow copy. Now, because we have a dynamic field, sometimes when we want to delete a message, we need to free this space also. So in this case, we need something that will delete a message, something like a destructor. So delete message. But the actual thing that delete will do is to release the space. Okay, so error messages. Once again, we change it. So we need to pass it by reference. And in order to do that, let's release the space. If message text different than null, free message text. Okay. And in order to say that we have released that space, we need also to change the pointer to null. Okay, null. So this is one way of saying we deleted the message, is that actually we release the space here, because otherwise if you lose this article, maybe you define it on a function stack, it will have that the text will remain in heap. So you will have memory leaks, and in the end that will pile up and you will have less and less memory. Okay, so we know how to clear an article. We can't actually delete the variable because it's a variable. Okay, it's not like an object. The variable will be deleted when that function stack will be released. Okay, so we know how to print a message. We have the structures for error messages, hash table. We know how to create a message, print the message, copy the message, and delete it. You see, it's very similar like with a class, but we are still in C. So you can find, let's say, equivalent functions for what we have done: constructor, destructor, equals, and so on. Okay, so I think that's all what we can do with an error message. Let's focus on the hash table itself. So the first thing that I want to do is to create the hash table. Okay, so I need a function, create hash table. And for that, we need an initial size. initial size. Okay. And let's do this. So hash table, h table. Okay. Let's create space for that initial space. So dot number of values equal initial size. And let's create space for that. H table dot table equals. So the values there are error messages. And the table, it's a pointer to error messages. Okay. Malloc. So initial size multiplied with size of error messages. Okay, now what's the size of error messages? What's the value of that?
8.
8. Why? Because it doesn't matter what's the text size. You have a pointer. The text will always be in heap. So an error message will always mean a pointer and an integer for the code. Okay, which means 8. That's okay. Okay, so here we created the table. We initialized the number of values. Let's return it. And we need something else to do here. And we know this from last week. Now, all the values here in the hash table, actually in the table, will be error messages, okay? And this is their number, initial size. And because we set this here, all our messages will have the text null and the ID 1. Now, if you forget to do this, and like I said last week, even if I'm redundant, I will always do that again and again in order to highlight something which is very important. And you can have the perfect implementation for all the other functions. Your program will crash because of this simple thing that you forgot or you missed. You forgot to initialize your values, okay? So in the end, all your function can be perfect, but if you forget to do this, you'll have a lot of runtime exceptions because you'll have pointers with 0xCCC. Your initial values will not be null, 0, -1, will be 0xCCC. Maybe if you are lucky, you will get 0. But don't forget to initialize your values. So how we do that? Int I starting at 0, I less than initial size, okay, I plus plus. We need to go through the table, H table. Let's open here brackets like this. So H table, index I, and now this is one error message. So equals -1, and H table at index I, text equals none. Okay. Now, in this case, this is redundant because I already set the values there when I have defined the structure. But once again, maybe you lose another 2 minutes just to be sure, rather than losing a lot of minutes later when you try to figure it out why you have a runtime exceptions. And the first candidate will be the last function that you have implemented, and you lose time finding the problem there, but generally the problem is not there. Okay. So don't forget to init your values. So in our logic here, we can check if a location in the table is free by checking either the text or, let's say, either the ID, because with we can have error messages without a message, but if the ID is -1, will always mean it's an empty location in the table. Okay. So let's add the main and start compiling this stuff. So build, rebuild, because we already have a lot of functions. So yeah, my usual problem with SDL, with the string copy. So just ignore me for this one. Define secure, and I refuse to memorize this. I will never do that. Even if I need to write this again and again for the entire semester, I will never memorize this. It makes no sense. So build, rebuild. Let's test the methods. This is a good practice. So error messages, error 1. Okay, so now we have an empty message. Now, if you want to initialize it like we have done earlier, like this, now you can't do that because you have a dynamic field. So you can't initialize the pointer. Okay, so this is not possible. Remember, every time we had the structure without a dynamic field, I always use this direct approach, but now that will not work because you have a dynamic field and you will take a pointer on a stack, and that's not okay. The first time you try to do delete, it will crash, but maybe you are lucky and the compiler will not allow you to initialize it like this. So in this case, we need to call, let's say, init message. And init message has another issue, but let's say here we agree with the shallow copy. We create here an object with space and we return a message. So here equals will give us a shallow copy. Okay. Now, generally here I will pass this by here or no. Okay. So here we will use equals. But let's say the shallow copy now, it's okay. So init message, let's say no CRT, whatever, secure. Okay. And the ID is, I don't know, 20. And let's duplicate this line. We have a second line to null pointer. Okay. And another ID 15. Let's print them. So print message error 1. And let's duplicate the line error 2. And I realized that we don't have a \n in print. Please add the \n because otherwise the messages will be on the same line. So here in print, just add here a \n. Okay, so now we will see distinct messages. Let's run this, Control F5. Okay, I will show you my screen. Okay, so error no CRT secure with ID 2015. Okay. If any of you has issues or you have questions regarding what we have implemented until this point, please ask me or ask your colleagues. So we are all okay. Let's create the hash table, if that's okay with you. Let's call it messages. Okay. And here create hash table, and let's go for the 101. Okay, the initial size. Because once again, we will double the size plus 1. And generally, we will use the modulo n hash function. Okay, so now we know how to print them and delete them. And this is the create hash table. Okay, let's continue. So what do we need here? We need a function that will allow us to insert a value inside the hash table. And here we will do probing. Okay, so let's start with insert. Okay, I will put a comment here. Insert into a hash table with probing. Okay, so in order to insert in a hash table, we need the function insert message. We need a hash table. hash table. And we need the message, error message. Message. Now, when we insert something in a hash table, is anything changing from the hash table perspective? And always check its structure. So when we insert something in a hash table, is this pointer going to change or the number of values?
Yes.
Why? We have an array of error messages, which initially has 3 locations. When we insert a new error message, we generally place the message on the right spot, right? But the pointer to the array is not changing. Okay,
Yeah.
we just play with the values inside the array. So when you are asking yourself, is that variable going to change? Always ask this pointer, hey, are you going to change? The pointer will say no. Now the array is going to change, but the pointer no. So we can change anything at that address in heap, and the changes are persistent. The real question is, do you change this pointer? And if the answer is no, no. Are these values going to change? No, because this is actually the number of available spaces or number of locations in the hash table, is not the number of, let's say, free spaces. So it will not change. It has no reason to change. So in this case, we can pass the hash table by value, okay? Because we don't change anything regarding the pointer table and the number of values. Okay, so in order to insert, we need to find the proper location for message. So for that, we need what? The hash function. Or yeah, let's call it get hash value. Okay, and here we need what? Key. Okay, and also because we need to adjust the hash function depending on the number of locations, once again we need n, okay, which is generally the size of the table. So here we do only this, return key modulo n, and that's it. This is the function, sorry. Okay, so the first thing that I will try to do is to get the hash value, which for us is an index. So int index equals get hash value for message.id and hash table number of values. That's our n. So now we got this. So probing means this. Probe the location given by the hash value, the hash function, and check if that location is free. If it's free, just copy the location or place your value there. It's an empty location, you can use it. Now, if the location is not empty, starting at this index, now probe the next one and the next one and the next one until you reach a location which is empty. So you will use that, or either you reach the end of the table. And at that point, you need to go back and start from the beginning, okay, until you reach a free location, or you get back here to the initial index. And that's the point when you need to realize that the hash table is already full. So you can't insert anything there. And another thing here, like we have done last week, is always check if the value is already present. Because you see, by probing, we once again go through available slots to the right of the current location. So in doing that, we can also check if the ID is already there. Remember, when we talk about a key, any structure that uses keys, the key should be unique. So we can't insert multiple values with the same key, because you will always find only the first one. That's the problem with keys which are not unique. If you allow them to be inserted, when you search for them, you will always find the first value with that key. You will never find the other ones, because you will always assume that the key is unique. So that's why you should always check. So here as a comment, let's say as return, we say -1 if the key is already present in the table, which means we already have it, and at return -2, sorry, okay, if the key, if the table is full. Okay, so in this way, we know that everything is okay. Now, if we return 1, if the value has been inserted. Okay, so we need to use this. Now, 0 is not used, so let's change the values here. So let's say 0 for this one and -1 if the table is full. So now we cover -1, 0, or 1. Okay, so let's start doing that. Let's start probing. How do I do that? I can write multiple ifs. Let's try writing a for. Let's be pessimistic. Let's assume that we will never be so lucky that the index location is empty. So I will do this. For int I starting at index I less than number of values, sorry, is hash table number of values, I plus plus. So this is the probing. Okay, it's a pessimistic probing. We assume that the index location will not be free, so we are already prepared to check the next one to the right. So if hash table at location index or location I, okay, because it's starting with the index, dot id is equals with -1, it's great. It means we found an empty location. It could be the index or the next one to the right until we reach the end. So we found the location for, so we found an empty location. So we just copied the value here. So we have what? Copy message into hash table dot table at index I from message. Okay, and we need to pass this as an address, so it will be like this. And now this applies to table I. Now, if you want to be sure that you get the address of a message, you can also write it like here in order to be sure that this will be evaluated in order to return a message. And after that, we apply the address to that. So we found an empty location, we copied, return 1, which means everything was okay. Now, else, they are different. Okay.
Sorry, I have a question.
Yeah.
Can you please say one more time why in the if we equaled with -1?
Here?
Yes.
Because when we created the table, you see it here?
Okay.
Now we have an empty hash table, right? Because it's just created. So how do we know from this moment on, after inserting several messages, which location in this table of messages is free?
Oh, yeah,
So,
the idea is...
exactly.
Yeah, I got it.
Because we will always choose a value which in reality has no correspondent. So here, I will put a comment. Is our assumption or our rule. So our rule for -1, it means it's empty. Okay, now it's okay.
Yeah,
okay,
yes.
So you will always need to do this. If you are not okay with this approach, then you can create for the hash table, but this will increase the complexity of your solution. Now you can choose in the end. You can create another structure like hash table location, And in that location, something like this, if you don't like to use the ID. So I can create this hash table location. In this hash table location, I will have an error message, and a boolean, boolean it's in Java, is empty, equals false. You see? And then your hash table will have hash table locations instead of error messages. And in this way, you can have your own method of flagging each location to be empty or not. Okay? So this is an alternative if you want to avoid using the ID alternative. So I will comment it. Yeah, I don't see the bar. Okay, so let's go back to insert here. So else means we are probing. The current location is not empty because it's not -1. So now I want to check if by chance the key is already here. So if hash table at index I equals, dot ID equals message dot ID, it means the key is already here. So return, what was -1. Okay, so now we covered the probing part, starting with index until the end of the hash table. Now, if we reach this location after this for has been executed, it means no of the two returns have been executed. It means we didn't found an empty location or found a duplicate of the key. So if we reach this spot, no available locations from index till end, table end. Okay, so what do we need to do? We need to start probing again, okay, starting from the beginning until the index. So generally, this will mean to copy paste the for here, but the only thing that will change is that I will start at 0 and I will be less than index.
I have a question.
Yes.
In the second if, when we're checking the ID with the message ID, can't there be a message that doesn't have the same ID that got there by probing because its spot was full?
Yes, that will happen. But you see, they will all have unique IDs, but the hash function will generate the same location. You will have a collision, right?
Yeah.
But now we are checking the ID, not I.
I was checking the message, not the index. If the message is there, not if the index is free, or yeah.
Yes, we check we check the message value at this location.
Okay.
So it doesn't matter if they have different IDs. Yes, you'll have collision. So we need to probe the next values, but they will have different IDs. It's clear.
Yeah, yeah.
Okay. Now, if you find anywhere in this table on any location a message with the same ID with the one that we want to insert here, that's not a collision. That's a duplicate key. We can't allow that to happen because you see what will happen if you allow this. The current location is full because the same ID, let's say, will give you the same location. And now you start probing to the right and you will find the next free location and you will insert a message there with the same ID. Now, when we will search for this ID to see what's the message there, you will always find the first one. You will never find the second one. It's clear, right?
Yeah.
Okay.
So I have a question after you finish. And then why we return -1? Because -1 isn't supposed to tell us that the table is full.
Sorry, is 0. Yeah, is 0.
Oh, all right, all right.
Yeah,
No
yeah,
changes. This
yeah.
changes everything.
Now it's clear for you. Okay, sorry for that. So
Yeah,
it's
for me.
0. Yeah, it's 0 if the key is already present in the table, right? Okay, so
Yeah,
0.
thank you.
Yeah, 0 is. Okay, so if this 4 has finished, it means only one thing. There are no available locations from index till the end of the table. So we need to start probing again from the beginning. And the first direct solution is to copy paste the 4, and that will do the job. Now, that will not look okay. Maybe with a while true, we can start again. Maybe you can find a different or a more efficient way without repeating this 4. We can also do here something different, but in that case, the exit condition will not work. So yeah, let's copy paste this. Now I have another way in my mind, but we need to rewrite this and I don't want to do that. So we start again. Let's say we start probing from the beginning. Now we start at 0, I less than index. We already check index. We don't need to check it again. So once again, we found an empty location. We return 1, else we found again the key, return 0. So it's the same 4. I just replace the initial value and the exit condition. So it's now index and 0. So now, if we reach this spot, the table is full. We didn't found any available location. So return -1. Okay, because this 4 will check from beginning till index. The previous 4 checked from index till the end. Okay, so the table is full. So this is insert message with probing. Okay, let's do the function that we need to check messages. Okay, so that will be get message. So error message, get message. Nothing will change here from the hash table. So we pass it by value, hash table, hash table. Okay, and obviously we need the ID, the message ID. So we will always search by ID. Okay, now here, let's say at return message with ID equals -1 if the ID is not present in the table. Okay, so this is our convention here. If the given ID, let's say given ID, is not present in the table. So let's create our error message. Result equals init message, empty string, and -1. Okay, so we start with an initial result. Here, the search can be also like here with 2, 4, but I will do it differently. So let's say while true. This is an infinite while. So we need to take care of that. We need to exit at some point because this will loop forever. Before that, let's get the index of the ID. So equals get hash value of ID and the hash table dot number of values. Okay, so while true, we check the index each time. So it will be like this. If we actually want to search that index and return the value there, but once again, we can find other messages with the different ID. So let's check for that. If hash table dot table at index dot ID equals ID, that's great. We just found it. Okay. Copy message into result. Okay. And hash table index. Okay. And break. Okay. We return from, we exit the infinite while. Okay. If this is not the case, else what? Increase the index plus plus. Okay, or plus equals 1 is the same stuff. Plus. Now, each time we are here in this while, now the index may increase forever. So here we need another exit condition. Maybe we reach the end of the table. So if index becomes bigger or equal, because we increment it, it can't jump, let's say, above the hash table number of values. So equal is sufficient. Now, if this is the case, once again, break. It means we reached the end of the table. We actually exit the table. So we need to break. Now, the only thing that this while true now is not checking is from the beginning of the table until the index is the second for that we have implemented earlier. So how do we cover that? Let's suppose here that index will be plus equal 1. So how do we know when we need to start from the beginning?
So we can check if index is bigger than the hash table dot number of values, then index should be 0.
Yes. And now it will start again from the beginning. And now we need another exit condition, because otherwise we will loop ourselves again and again from the beginning.
We can have another integer to save the first index.
Yeah, the initial index. And here we should always check if we reach the initial index.
Well, we can just add an if the initial index is, if our current index is at the initial index, we just break after all this.
So I will define an initial index, right? We need this value here. So where do you want to put the if? The if index equals initial index?
At the end.
At the end. So if index equals initial index, break. It means we got from where we started. Now let's see. We don't want to break after the first iteration. So this is my concern here. Let's see if that will happen or not.
It will not break because in the if before we are incrementing the index.
Okay, so we start initially with the index with initial index value. This will not be the case. Okay, so this will be ignored. Now we check if at that location we have an ID equals with ID. So once again, here you see equals ID, we copy the message break. So if we find at that location the ID that we are searching for, we copy the message into result and break. Now else means the index will be increased by 1. It means at that location, initial location, we already have a message, but its ID is different than the one that we are searching. And index will be +1, yes, and this will never happen here. Now, this will go until we reach the number of values. Index will start at 0. Once again, we check all the values, and at some point, we will be right before the initial index. This will become the initial index, and now we get out. Another thing here, we didn't cover the particular case where the initial location of the index is empty, because if that's empty, there is no, do we have any reason to search for others? Yes, maybe we have, because maybe we had a collision and maybe we deleted that collision at some point. Yeah, so yeah. I was thinking at this, maybe that location, it's an empty one, which means the ID there is -1 based on hash value. So do we have any reason to search? But I was thinking at this alternative scenario, let's suppose we insert a lot of messages in the hash table. Some will generate collisions. So we will have a different message with the different ID, which will occupy this location. Now, the message with the search ID will be inserted to the right of that location. And later, maybe we decide to remove that message with a different ID that was placed here, because it was a collision. So at that moment, you set the ID -1. This is deleting the message. So yes, the message is still in the hash table, but is to the right of that location. So that's why we still continue to search. Okay, so I think this will cover all the possibilities. Let's check this. So create hash table. Now let's insert the tables, the messages. So I will have what? Insert message, where? Into messages. Okay, message 1, error 1, sorry. Error 1. Okay, duplicate the line, error 2. And now let's search for them. So here I want to print. Yeah, I forgot again. Return result here. Okay, it's the search, the get message. Return result. Okay, and the result is initially -1. If we found it, we will copy it here and we return the result. Okay, so print error, print message of what? Of get message, hash table, which is messages, and ID, let's check for 15. Control D, let's also search for 20, and Control D, one other one that doesn't exist, like 53. So Control F5. So these were the initial messages. And now this is what I got from the table. And this is for, it means it doesn't exist, ID -1. Remember, it's our response. It means we don't have anything there. Okay. Now let's try to simulate a collision. So we have 101. So in order to create a collision, let's create another message, and this will be our collision. Okay, so this will be error 3. And in order to generate a collision, 101, it means for 20, it's 121. Right? Because 121 modulo 101 is 1, and the remainder is 20. So it will give us the same hash. So let's say this is a collision for 20. You see, the messages have different IDs, but they will generate the same hash value. So let's insert this message also. Error 3. Now let's search for this one here. Control D, 121. Just to see this more clearly. Backslash. Okay, so this is our search part. Control F5. Okay, so yeah, Control F5 again. And I will share the console. So they are here, okay? Error null pointer with ID 1520. And in order to see that we will not allow inserting the same message again and again, I will try to insert it here and take the code. Int result code equals, I'll try to insert the same message again. Printf result code for inserting error 2 is 15. And here %d and result code. So once again, run it, Control F5. So it's 0. Okay, you see, because it means it's already here. And for the others, everything works as before. Now, what do you need to add to this example in order to finish it? I will just add the to-dos here. So in order to finish it, you need to add 2 functions. And this is another function that we needed last week, but we didn't have the time to do it. So to do a function to resize. So resize the table. Okay. Another function that is needed here is checking the how many spots are available. Okay. So a function that will compute, okay, the, let's say, percentage of free locations. Because you need here a function that will compute the percentage of free locations. And Mihai, I think he told you during the course that you need to do this check from time to time, because generally, let's say 70%, or if this is the percentage of free locations, if you go under 30%, let's say you need to resize, because otherwise the probing will eat up a lot of time, because you will go through the entire table to find spare locations. They will be very few. So let's say under 30%, you need to resize. Generally, you need to resize. Okay, and in this way, you don't waste time by searching 1 or 2 remaining locations in a huge table. Okay, and the last method is to do a function that will delete. Now remember, this is a logic delete. You can't actually delete the location, remove it from the array. It doesn't make sense. A function that will delete, logic delete, a message for a given ID. Okay, so it's a logic delete, which means you leave the spot there, the location, but you mark it as free, as being free. And we know how to do that. You set the ID to -1. And the next time you will get a collision or a new message there, you will use that free location. Okay, so this is probing. Okay, and with this one we cover all different implementations for a hash table, probing versus chaining. And next time, I suppose you will cover heaps, the heap structure, or it's also known as a priority queue, which means at any moment you will get very fast the messages or any value with the, let's say, the highest priority. That could be a field, and based on that value, you will always get instantly the values or the articles with the highest priority or with the lowest priority, because you can have priority queues for maximum or for minimum. It depends on what you need. So I think this will be the next topic